Hello everyone and welcome to today's webinar. My name is Mark Dignam and I'm a product manager here at aPriori. Our topic for today is additive versus traditional manufacturing. What's your best option? We will be highlighting some of aPriori's additive manufacturing capabilities and talking about methods and considerations for comparing additive and traditional manufacturing on your components. Before we get into the content, I'm going to open a quick poll. So we want to understand how you are currently using additive manufacturing within your company. Note that you can choose more than one of these options that we've put up here. So we're wondering, do you use additive manufacturing currently to make prototype parts, to make fixtures, to make production parts, to make service parts, or not at all? Let's take a look at the results of our poll. So it looks like, wow, a lot of you are using additive for prototype parts, and a fair amount, actually a surprising amount, are using it for production parts and fixtures as well. So that's very encouraging. I'm happy to see that, and I am confident that you guys will learn a bit about how to utilize aPriori when evaluating those production parts and fixtures during our session today. All right, so let's move on to our content for today. First, I just want to go through a brief agenda. And before I get into the agenda, I just want to mention that I am joined today by David Knackel, who is going to be going through the bulk of our content today. David is a cost modeler based out of our Belfast office. David's the lead cost modeler for our additive manufacturing processes, and he's very, very knowledgeable of our additive cost models and additive capabilities in general. He's going to give you an overview of the various additive manufacturing processes that we cover in aPriori, and then also give you a couple different demos of how to utilize aPriori to cost additive components and see some of the key details. And then finally, I'm going to wrap things up with a high-level discussion of trading off additive manufacturing versus traditional manufacturing, some methods that you can use to do that early in the development process. All right, so before passing over to David, I just want to give a brief overview of aPriori's additive capabilities. A little bit of history of additive manufacturing at aPriori. It actually started around 2011 in the product as a process group called rapid prototyping. Additive manufacturing wasn't really used for production parts very frequently within our customer base back then, so we really just addressed a couple of rapid prototyping capabilities and hadn't touched it for a while until you guys started letting us know that you had a lot more interest in additive. So in 2017, we made some investments into our cost models and into our capabilities, and we made a couple of large changes. So we moved our process group from rapid prototyping to additive manufacturing, and we started to build out a bit more infrastructure. And as of 2018 R1, we now cover 4 major additive manufacturing processes. So direct metal laser sintering, commonly referred to as DMLS, selective laser sintering, commonly referred to as SLS, material jetting, and stereolithography, or commonly referred to as SLA. You'll notice that acronyms are very, very common within additive manufacturing, and they can be a little bit tough to keep straight now and then, but those are the processes that we cover in the product. And David's going to talk about them in more detail, but generally DMLS and SLS are the primary production methods for making metal and plastic production components for additive manufacturing, whereas material jetting and SLA are mostly focused on producing visual prototypes. And in terms of our capabilities, just like all of our other process groups, we can read any standard CAD file to help users develop a very detailed cost estimate very quickly. Now, one thing I want to point out about additive manufacturing is that we do not read STL or 3DX files or any of the faceted models quite yet. I know that they're common within the additive development chain, but they're not model types that we can read in yet, just standard CAD files. And our additive process group, it supports several of our typical use cases. So early design decisions, such as determining if a part is actually a good fit for additive, which we'll talk about in more detail near the end of this webinar. Design to cost, so costing various iterations of your design as it progresses to understand the impact of those design changes. Am I requiring more support structures? Am I requiring more build time? Starting to take a look at the impact of those types of things. And then finally, supplier negotiation. Just like our other cost models, we expose a tremendous amount of detail that can really help negotiating with suppliers, especially in this newly emerging field where a lot of the knowledge bases are not quite as built up as more traditional manufacturing models. So in order to support those use cases, we have several key features that are very important. And David's going to get into these in more detail, but some of them are, just like our other cost models, our manufacturing cycle times are calculated based on physics-based cycle time calculations. Also, we do extract a build direction and we assume a build direction, but just like draw direction in plastic molding, users can very quickly override the build direction that was selected and understand the cost impact of going with different build directions. It can have a big impact on performance, and as you see evaluated in aPriori, it can have a very big impact on cost since it changes the build height, the number of layers that you need, the support structures that are required. And another thing that we do identify are support structures. So we automatically recognize where support structures will be required, and we account for the time and cost to both print those support structures and then also remove them from the part, which can be a very time-consuming and costly operation, especially when you think about metal support structures for a metal component. You're basically breaking a metal component in half, which can be time-consuming and a very costly process. Now that we've talked a bit about aPriori's additive capabilities, I just want to give an overview of additive manufacturing in general in terms of the pros and cons. So probably the biggest pro of additive manufacturing is the geometric flexibility that it provides. Additive manufacturing works generally by building a part up from scratch. It starts as nothing and you print up layer by layer to create your final geometry. And what that means is it gives us a lot more flexibility in terms of the features that can be made. You don't have to worry about that feature being accessible from the exterior of the part to be reached by a machine tool, right? You can build a lot of internal structures without being able to actually see them from the exterior of the part, which gives us a lot of flexibility. For instance, that part that we see in the bottom left-hand corner would be pretty easily manufactured with additive manufacturing. However, within traditional manufacturing, trying to make that part would be very, very difficult. Some of the other pros that we have are the fact that there's very short turnaround times and there's little to no investment costs required because it's basically just a machine program that's building up this part. You don't need to spend time programming very complex machining cut paths or building a tool to make the net shape of this part. Now, there are some drawbacks in terms of additive manufacturing. First of all, cycle times are pretty slow. Additive is not a great fit for larger production volumes yet, although the technology is advancing very, very quickly. We saw last year, HP came out with their multi-jet fusion machines, which should be accelerating the production of plastic parts pretty quickly, and Desktop Metal has some promising technology within the metals capabilities as well. But as of right now, cycle times are still quite slow. Secondly, materials are still quite expensive and somewhat limited. So materials either need to be purchased as a powder or purchased as a form that's specific to an additive process or an additive machine. So there's a lot of specialized manufacturing that goes into making those materials, which makes them quite expensive. And because this is still a pretty new area, a lot of the more exotic materials haven't been explored or tested yet. It's rapidly changing, but just not all materials are quite available yet. And finally, in terms of drawbacks, large parts are quite difficult to make currently because the build volumes on these machines are still fairly small. So in order to make large components, they often will need to be manufactured in multiple bits and then fused together. So in terms of main cost drivers that we see within additive manufacturing, because the materials are so expensive, material cost is generally going to be your biggest cost driver for most parts. In terms of actual processing, your build time, so the time to actually print up the part, is going to be a significant cost driver as well. And that's typically driven by the size of the part, so how much volume do I actually need to print, the thickness of the layers that you're printing, so the thicker the layer, the shorter your build time is going to be, but the worse the resolution of your part is going to be because you're printing thick layers. And then finally, machine capability, so machines vary pretty widely in the speeds at which they can actually manufacture parts. That's going to have a huge impact on build time. And finally, the last big cost driver that we have are support structures. So I know additive is frequently talked about as pretty much a hands-off process, that's a bit of a misnomer. So support structures can be a big cost driver because they not only need to be printed, but after the part has been printed, they need to be removed from the part, and any connections to the part need to be smoothed out to get a decent surface finish. So they can have a pretty significant impact on cost. All right, so with that overview done, I'm going to pass it over to David.
Hello, everyone. So the first of the 4 processes I'm going to talk about today is material jetting. So with material jetting, photopolymeric droplets are deposited from a printhead, and on the same printhead there is a UV lamp, and as the droplets are deposited, the UV lamp almost automatically solidifies and cures the droplets, and this enables the part to be built up layer by layer in the vertical direction. Most of the parts that can be made with material jetting are non-functional prototypes, and it's excellent for making parts where visual and haptic properties are required. Some of the advantages then of material jetting: support structures are very easy to remove, and with certain materials they're dissolvable. It can produce parts with a very smooth surface finish and very high dimensional accuracy, and these are comparable to injection molded parts. And some of the disadvantages then: support structures are always required no matter what the overhang angle. I'm just going to talk a little bit more about overhang angles and support structures later. The parts tend to have poor mechanical properties, and the materials are photosensitive, so that means the mechanical properties and color will degrade over time. So we've got a few images of examples of material jetted parts. The first one is this trainer or shoe, and it just demonstrates the color range that can be gained with material jetting. So there's literally hundreds of thousands of blends of colors that can be made with the latest material jetting printers, and this also demonstrates the range and hardness as well. So the bottom of the shoe, the sole, is quite firm, and then on the upper part it's more flexible and soft. This anatomical replica demonstrates the levels of transparency that can be had with the different materials, so from fully opaque to translucent, then to fully transparent. And then with these razors, you can see that the frame is actually rigid, but also printed from the same printer is a soft gel-like to help with grip. Material jetting in aPriori is represented with the following routing. So the first process is printing, which is literally, just as I've explained, the printing of the part. And then break off, this is the process of removing support structures from the part. And in our VPE, or virtual production environment, we've got a range of material types: rubber-like, ABS-like, polypropylene-like, and a couple of the big machine manufacturers as well. And with material jetting, the parts can go up to a size of 39 by 31 by 19 inches. The next process is stereolithography, or SLS. And this time, again, we're using a photopolymeric material. Only this time it's not being deposited from a printhead. It exists in a vat, and a UV laser cures it on a layer-by-layer basis. The parts are typically form and fit prototypes, and for parts that might be wanting to test for visual, ergonomic, and aesthetic properties. The advantages are that a smooth surface finish can be attained without actual any finishing processes. Very high dimensional accuracy. There's a fine detail that can be achieved with stereolithography down to 50 microns. And one of the big advantages is the part size as well. So parts up to a size of 1.5 by 0.75 by 0.5 meters. The disadvantages with stereolithography are the parts can be brittle, and because they're support structures, they require some post-processing to remove them and to remove any stumps left on the part. And just the same as material jetting, the mechanical properties and color can fade over time because the material is photosensitive to UV light. Again, some example parts. This shows that we can, some of the materials are translucent. This image shows that the degree of surface finish and the high detail that can be achieved with SLS. We've got a decent range of colors as well, and the support structures that are printed are very fine and can easily be broken off. In aPriori, we represent SLS through the routing shown in this image. So resin curing is the process of SLS essentially. Again, we've got a break off of support structures. And part curing for stereolithography parts, the part comes out of the printer and it's said to be in a green state, so it's not fully cured. So To enhance the mechanical properties and to ensure the outside layers are solidified, the part is cured in UV light. We've got 5 different material types, 2 of the big machine manufacturers, and large part size up to 59 by 29 by 19 inches. In selective laser sintering, this time we use a fiber optic laser, and instead of there being a vat of resin, it's a container of powder. It's one of our 2 powder bed fusion processes, and the powder is a plastic or typically nylon. And the big advantage of this process is that no support structures are required. The process can be used for form, fit, and functional prototypes, and features like living hinges, functioning springs, and snap fit components can be made with this. As I mentioned, the big advantage are that no support structures are required, so this reduces material cost, reduces cycle time, and allows for more complex geometries. And another advantage is that it actually allows for 3D nesting, so we don't need to worry about support structures between the bottom of the part and a base plate, so it will be allowed to nest in a 3D manner. The parts have good isotropic mechanical properties. That means that properties are the same in all directions. And unlike SLS parts, which are brittle, these parts allow for machining, tapping, and drilling. The disadvantages, as can be seen in this image on the left, is that the part surface can be quite grainy. And then it also has internal porosity issues. So the part, if you're looking to be watertight, it's going to need an extra it needs an extra post-processing operation, so silicone coating or dip in some coat of lacquer. But typically a nylon material is used, and that produces white parts as seen in the image on the right. So SLS in aPriori, it consists of the laser sintering process. This is the sintering of the part. Cleaning, which is removing powder from in and around the part. So this is represented as either compressed air or dry ice, depending on material. And because it's a powder bed fusion process, we have to consider powder. So we've got 2 processes for that: sieving, which is to remove the damaged powder, and powder loading to put new powder into the next build. And we've got a no-cost feature process here, which is essentially we're assigning support structures to no-cost feature, so there's no cycle time or cost associated with them. We've got a range of materials, and a lot of them are nylon-based, so glass-filled nylon, metal-filled nylon in SLS. We've got 2 of the big machine manufacturers, parts from 29 by 21 by 21 inches. And again, just to reiterate, support structures aren't included in this process. The last process is direct metal laser sintering, DMLS. So this is the most common additive metal manufacturing process. It's very similar to selective laser sintering, with the obvious difference being that it's sintering a metallic powder as opposed to plastic powder. It can be used for form, fit, and functional prototypes, and there's 20,000 different DMLS parts in Boeing's aircraft range, so just goes to show you the extent to which it can be used in production. The advantages are that the parts are strong and durable. They're 99.8% dense. They can be assembled parts. Assembly parts can be made from a single component, and there are a variety of materials for different applications. The disadvantage when compared to traditional manufacturing, as Mark has already explained, is it's maybe not suitable for large batches compared with traditional manufacturing, and it requires support structure removal and some extra machining to achieve the fine tolerances. So we've got a couple of different example images. The parts on the left are dental implants, bridges and copings, and they're made with a cobalt chrome alloy. And we have some of them in our VPE. And the part on the right is the SpaceX's Super Draco engine. It's a combustion chamber which is made of an Inconel super alloy. We've got a couple of them in our VPE as well. DMLS and aPriori is represented, firstly, working from left to right, this metal sintering process. We've already explained that. Powder recycling, again, is a powder bed fusion process, so we account for powder sieving and powder loading. And because the parts are printed on a base plate, we have to consider removal of the base plate, and that's done with one of 3 options. The first one is manual tool base removal, and that is essentially a hammer and chisel to remove the base plate, one of the more cruder options. The second option is using a hand tool like an oscillating saw, a power tool, to remove the base plate. And the third option is the default option. It's wire DM removal. Also automatically included with DMLS is ultrasonic cleaning. So to remove the powder is very dangerous if it's inhaled. So this is done in an ultrasonic cleaner. Also, as we mentioned, the base plate's removed, but after it's removed, it goes through a facing operation. So we use a 3-axis mill with a facing tool to skim the top surface and get it ready to be reused again on the metal sintering machine. And then finally, to relieve residual stresses, we put the parts through a stress relief process. That's done on a radiation heating furnace. In our VP, we've got a good range of different material types for DMLS, and we've got 5 of the larger machine manufacturers in some of their machines, and parts up to 31 by 19 by 15 inches can be made. I touched on support structures earlier, and I just wanted to make sure we're all familiar with them. So stereolithography support structures are typically look like tree-like support structures, and they've got a very thin point on the end to make them easy to remove. With DMLS, we've got a lattice type support structure, and not only are the support structures used for anti-gravity purposes, they're also used for heat transfer to remove heat down towards the base plate, which improves the surface finish and reduces powder damage. And then with material jetting, the support structure is a separate material from the part, and it's 100% dense, so it's not a lattice, and it's required on all overhead angles from zero from horizontal. So this next slide might help explain that. So going from left to right, any overhangs as they get bigger will typically have more issues on the underside of the overhang, as this image demonstrates. And then with overhang angles, typically 45 degrees, anything over that from horizontal is fine. But as you go down to 30, 22.5, 15, and 7.5, as this image shows, you start getting problems on the underside edge of the overhang. And then the similar thing is with bridges. You get drooping as the spacing increases between them. These images are for fused deposition modeling, but the principles apply to any additive process that uses support structures. So hopefully that makes a little sense of why we use them. So key cost drivers, this part has been costed in direct metal laser sintering. So aPriori can produce a cost summary, and this part, the fully burdened cost is $169.13. And we also produce a cost by process. So our metal sintering process accounts for 61.8% of the cost. And I just want to demonstrate that it's not really just a simple print and go type process additive. There's a lot of post-processing required, and even the wire EDM itself accounts for 22.7% of this time. So there's a lot of post-processing. And then the cost by category, material is the biggest contributor to that, and that's quite typical across additive in general. The reason for that being in DMLS is our finished mass of the part is only 0.2 kilograms, but the rough mass is the actual amount of powder that has been used to create this part, and it's 0.65 kilograms. So inclusive of that is the finished mass, powder that had to be recycled, support mass, and then waste mass as well. So that figure is 31%, the finished mass over the rough mass. And then typically our labour and direct overhead coming from cycle time are also large contributors. So I just want to jump into the software and show how a design engineer might interact with aPriori. So the first thing I want to show you, this is additive manufacturing, and we're in DMLS, and again this is the part that was costed earlier, and we're using an aluminium alloy. We've got an image on the bottom right hand corner, which is our nest, that tells us the material and the build plate size, and we can fit 5 parts onto this build plate. And then up in the manufacturing process panel, we've got 4 different process groups that are being used. We've got additive manufacturing, machining, heat treatment, and other secondary processes. So a design engineer can just work down through the manufacturing processes and see exactly what's happening to this part. So within additive manufacturing, it's DMLS, so it's a powder bed fusion process, DMLS. And our first process is metal sintering, and underneath that we can see the as sintered operation, and that's telling us that all of these different GCDs or features in this part are sintered, so that essentially this part is completely sintered. And then our powder recycling consists of sieving and powder loading. And then break off, This is applied to all our support structures. The support structures are shown in purple underneath the part. And then a design engineer will be able to apply some design guidelines to the part. So we've got 4 simple holes on the outer edge, near the outer edges of the part. And one of the design guidelines for horizontal holes from the build direction, if they're less than 10 millimeters, they don't actually need support structures. So what we can do is we can go down to these GCDs, for example, support structure 66, and edit the operation. And rather than be going through the additive manufacturing process routing, we can assign this as a no-cost feature. And that means that, again, cycle time and cost won't be associated with this. Then going into the machining model, there's 2 3-axis mill processes. We've got our base plate facing operation associated with this build direction, which is the green arrow. So if you can imagine underneath this part, there is a build plate. It's almost like a virtual part that we can't see in the user interface, but our cost model is taking that into account. So base plate facing operation is performed in that, which is getting it ready for the next set of parts to be built on it. And then another thing a design engineer might want to consider is that some features in this part are fairly critical. So, for example, these 2 holes might have a shaft going through them. So simple hole 1 and simple hole 2 down here can have a tolerance specified against them. So we can change the tolerance to 50 micron. And what that does, the model picks up that DMLS does not have the capability to produce this tolerance, so it automatically assigns machining operations, and in this case it's going to assign some hole boring, accounting for 52 seconds each. And then also we've got our stress relief process under the heat treatment model and ultrasonic cleaning underneath the other secondary process model. So one other thing a designer could do is review our cost by category again. And again, material is accounting for the largest portion of cost, 38.7%. So if we go down to the material underneath the cost guide and we expand that, we can see that our material cost is $100 per kilogram. So that's $100 per kilogram of this aluminium alloy powder, which is high compared to bar stock in aluminium. So a designer can then open up our stock machining model and go in and assign aluminium, one of the aluminium alloys, so 1050 for example. They're all a similar cost. In this case, it's $9.84. So it's a lot cheaper than the aluminium powder. And I'm going to just jump back into the PowerPoint again, just to show the comparison. So comparing the additive, aPriori can produce a cost comparison of additive manufacturing of this part and stock machining. And the first thing to note is when you do that the stock machining cost is 44% greater than the DMLS part. So the material cost, again, $100 per kilogram for the powder in DMLS, $9.84 for the stock in stock machining. If we look then at a breakdown of material coming from the cost model, the finished mass is the same. It's 0.2 from the DMLS model. It's 0.21, that's a rounding error in the machining model. But then the rough mass is greater, far greater in stock machining. So it's over 4 kilograms in the stock machining model and only 0.65 kilograms in the DMLS model. So our utilization, powder utilization, our material utilization is far greater and better with DMLS. So that means that the material cost for DMLS is $65 per part, and it's $40.44 per part for stock machining. So rather than being 10 times cheaper, it's actually only 1.6 times cheaper. And it would be fair to say that the hypothesis that this would mean a cheaper part based on material cost isn't necessarily true. Other large contributors to cost here is in the labor. So with DMLS, we have 45 minutes of labor time, and then within stock machining, we have 3.5 hours of labor time. And then our amortized batch setup, $2.13 for DMLS, and it's 700% increase for in machining. So our production volume here in both them scenarios was 500 parts over 1 year, which roughly works out at about 41 parts per batch per month. And our setup time is only 2 hours for DMLS, but for stock machining it's 20 hours. So the production volume suits DMLS a lot better. And that's a big contributor. If we have more parts in traditional manufacturing, like stock machining, this would be amortized, the 20 hours would be amortized across a lot more parts, and it would be better suited to the stock machining. So if I can just open up the software one more time, and this time I'm going to show how an additive manufacturing cost engineer might interact with the model. So we've ascertained that DMLS is a better option than stock machining. It's cheaper, but maybe there's a further chance to reduce the cost of the parts within DMLS. So if you notice, remember that there's 5 parts within the original DMLS model in the nest. But what we can do is use this build direction tool, and if we hover over different faces, or one of these faces, X, Y, or Z, we can assign a new build direction. And so an expert might say, well, there's actually less projected area when the part is orientated in this direction, and that would be true. So I've assigned the build direction against this perpendicular to this face, and what it does is produce 9 parts on this machine. Yeah, so just going to jump back into the presentation and compare them. So the scenario was changing the build direction so that we've got 5 parts, and now we've got 9 parts. So what we can see is that the cost actually has went up. It's went up from $169 to $224, so that's about a 32.6% increase. And starting with our material cost, the finished mass is still the same, 0.2 kilograms, but again, we see that the rough mass has went up. It's went up from 0.65 to 1.03, and our material utilization has dropped from 31% down to 20%. So the material cost has moved from about $64 per part to $103. That's a 60% increase. And the reason for that is that we have now made more support structures by changing the build direction. So by making more support structures, what we've also done is increase the amount of time, labor time associated with removing them support structures. So our labor time has increased by 73%. And also by making a bigger nest, our wire EM process now has to remove more material as well. So there's an associated increase in labor time with that. And it might have seemed like a good idea to go from 5 parts to 9 parts because you'd be amortizing some of the setup across 9 parts rather than 5 parts. But we can actually see from the direct overhead and amortized batch setup that it's actually a very small reduction. It only reduces the setup times by about $3.54 per part, which is it's not a great contributor. An additive cost expert also has a few other ways that they can interact with the cost model and change cost. So there's a whole lot of PSOs, process setup options, too many to go through individually, but first one here is layer thickness, and by default on this particular machine that's being used to cost the part, the default layer thickness is 50 micron, but we have capability from 20 to 80 micron. So if we change the default and entered in 80 micron, there is an impact straight away on cost, and it reduces the cost by about $13 there. We have nesting length, which is the distance between, we specify that between each part in the nest. And we've got a whole load of different setup options like loading and splice time, purging oxygen from the system, fitting the build plate, which all contribute to the setup time. And then certain machine variables can be changed, like the time it takes for the recoater blade to coat powder over the build chamber. There's a lot of them here, including cool time and heat time as well, and a lot of different ways an expert could interact with this model. So I'm just going to pass it back to Mark to discuss a comparison against traditional manufacturing.
Great, thank you very much, David, for explaining that detail to us. So I'm going to back things out a bit and talk a bit about how we can compare additive manufacturing to traditional manufacturing, specifically focus really on early on in the development process. But before I talk about some of the details of how we can actually do that, I want to share some insights that we've found as we've been working with additive, and that is the relationship of cost versus complexity. And this is a little bit strange to understand at first, but I'll explain it a bit. So basically what we've seen is that as additive manufacturing parts get more complex in certain dimensions, their cost can actually decrease with that increased complexity, whereas machine components, as you increase the complexity, almost always their cost is going to increase. And there's a point where those two lines are going to cross. That depends on the complexity and the batch size and annual volume that you're working with. But this is a pretty simple example. Starting off with a simple block with a single slot on it, you can see there's a very wide difference between additive manufacturing and machining. And then as we add in more features, so for instance, we've added some slots and some milling around the perimeter, that gap starts to close, additive becomes cheaper, and machining becomes more expensive. And the reason for that is, first of all, for machining, you're assuming that this block is staying the same bounding box dimensions, you're still going to be using the same amount of material, and all that you're doing to get this more complex shape is spending more time machining away that material that you're already paying for. Whereas for additive manufacturing, right, to make this part versus this part, it means less material is required to be deposited, which means less material costs, and it also means less build time is required to actually produce that part because you're printing less material. I thought this was a pretty interesting example that explains, as parts get more complex, they're going to be a better and better fit for additive manufacturing, right? If you're just making blocks of aluminum with simple holes in them, traditional manufacturing is pretty good at doing that. But as you start to get into more complex geometric shapes, that's where additive starts to become a much more reasonable thing to look at for manufacturing those parts. All right, with that in mind, I want to talk about evaluating designs for additive at a high level. There's many different classes of parts that are very good fit for additive, but the three I want to talk about today are listed here. So first of all, parts with very high customization. So this is an example of a shoe that Adidas is working on, that actually this is a product line that they're proposing that is going to be custom shoes for each individual person. So you get essentially a scan of your foot, and you get a running shoe that's printed to support your foot exactly the way that your foot is. So that's going to be a different part for every single person. And while that example, and no, Adidas is not on the call, but you guys, I know a lot of you have very customized components within a lot of your products, be it components that have different customers' logos on them, or components that you're looking to customize for similar things like grips that are specific to different hand sizes. Those types of things with lots of variability are very good fit for additive, because changing the part design slightly to account for different ergonomics or different logos with additive manufacturing is pretty cheap. But if you're doing that in injection molding, or you're doing that in machining, it requires a new tool or a new complex cutting path to be designed, and takes a lot of setup, whereas for additive, it's pretty quick to make that change. The next topic that I want to talk about for high-level, very good fits for additive manufacturing are assemblies that are existing that are performing a single function. So this assembly that we see here, this is a three-component design with many different fasteners to mount those three components together. And really all this is doing is this is a weld fixture on a welding table. And the reason why it's designed like this is for clearance from other parts, and to make this out of a single part out of traditional manufacturing would be much more difficult than making it out of three parts. So they decided to break it down into three parts. Whereas for additive manufacturing, manufacturing that complex shape that needs to be created to connect those various mount points that we have on this part, it's pretty simple, right? We've talked about how complexity within additive manufacturing is very, very achievable. And so by changing their design to go to additive, this company not only reduced their part count significantly, going from 3 manufactured components to 1 manufactured component, they're also removing a lot of additional hardware. They're removing a lot of potential sourcing issues by having to source those 3 parts to potentially 3 different manufacturers, removing the assembly time. And they're also seeing significant weight reductions, right? There's a lot of wasted material sort of in the middle of these components. So by going to additive, they were able to reduce the weight significantly. And they also are expecting to see some downstream impacts from reducing that weight. So this, as I mentioned, is a fixture that goes on a weld table that's actually rotated by an engine. They're assuming that that engine can be reduced in power by using these lighter fixtures because there's less mass to actually rotate around. So lots of downstream benefits potentially realized from lightweighting this part by going to additive. The last topic that I want to talk about in terms of high-level categories that are very good fits for additive are highly machined components. As we talked about in the previous slide, this is a specific example of a hydraulic valve that on the left-hand side, we can see this is the machined component, and there's a lot of machining going on in the internals of this valve, obviously, to get it to function properly. And then also you can see it's just a block of essentially wasted material that's just sitting there, not really doing anything functionally, just adding to the weight of the component. So by moving to additive manufacturing, this company was able to maintain the same performance out of this valve and reduce the weight by 60% by changing the geometric design of this part, but also because of the geometry that could be attained using additive manufacturing. They were able to look at a different material that also allowed them to lightweight this part pretty significantly as well. So those are some classes of parts that, if you have them within your product line, would be very, very good starting point for looking at moving them to additive manufacturing. And I'm sure that all of you have many parts that fit into these various categories. When evaluating designs for additive manufacturing, it is pretty important to do that evaluation as early as possible. And the reason being, the design that you're going to actually get out of designing for additive is potentially going to be much, much different than the design that you would get going with casting or going with machining, for instance. This is an example from a design competition that General Electric ran several years ago, where they had various design engineers design a component for additive that fit into this basic outline and met certain performance criteria. And this picture that we see in the bottom left-hand corner is actually the final design that was used for the additive manufactured component, which, as you can see, is very, very different than the way that you would potentially design that component for machining or casting. So the earlier that you can make the decision to go to additive, the less design cycles that you're going to burn designing for machining or designing for casting. And as much as we'd like to think that cost is the most important thing for you to look at, it's really not when you're deciding this early, right? You need to not only consider cost, which we can help you with, but also performance, the quality, the turnaround time, and the long-term cost impact. So if I'm going with an additive component where I can reduce the weight by 20%, and this is a part that's going on an airplane, what's the long-term impact to the fuel consumption that we're going to get by lightweighting this part? So those are the types of things that should really be taken into consideration in addition to the costing that we're talking about. Now, in order to facilitate that early costing, obviously a precise cost would be nice, but really to do that early evaluation to determine if additive is an economically feasible path to go down, you really need a rough order of magnitude cost estimate. So you could go off and design these various components for the various manufacturing processes, but that takes time, and it's really an extra level of detail that's not quite needed for a rough order of magnitude estimate. So in order to facilitate that rough order of magnitude estimate, we've outlined some steps for actually doing that. Step one would really be to create a rough model for traditional manufacturing. So that would be what we see in the upper right-hand corner. It's pretty rough. It could be machined, it could be cast. It's not exactly what that final part is going to look like, but it's close. And then step two would be to create an additive model, a pseudo-additive model. So to do that, you take this traditionally modeled part and shell it to a reasonable thickness in terms of what type of thickness you think you could get to maintain the performance by going with additive. 25% is a good example. And this can be done with not only individual parts, but assemblies as well. So take that three-piece assembly that we talked about earlier. You could shrink wrap that whole assembly, save it as a single body part, and then shell that new part that you have to a reasonable thickness to have something that you could cost in additive as a single component. And then the next steps are pretty straightforward. So you'd cost the pseudo-additive model and traditional model in aPriori, and that can be done either interactively, as David was showing in his demo, or it can be done via bulk costing if you have a whole batch of parts that you want to look at once. And then on top of that, because we're dealing with simplified models, you want to make some additional assumptions to sort of fill the gap in terms of where you would expect to get to with your final design. So let's say for this specific component. We might have 50% more cycle time by going with a fully machined model, or we might have 20% higher casting tooling costs, or our additive mass might actually be 20% lower than what we calculated based on our simple shelling. Once we apply those assumptions, then the last step is to create a comparison and then use that information to help us make that decision, taking into account things like performance, like weight savings, like long-term cost benefits. All right, so just to summarize what we've covered today, so generally additive manufacturing can potentially help you increase performance of parts while reducing weight, part count, complexity, and turnaround time. And within aPriori, we support many different use cases, a lot of different levels of detail and different levels of override for 4 key manufacturing processes: DMLS, SLS, material jetting, and stereolithography. And it's really important to evaluate trade-offs as early in the design process as possible to determine your design direction so that you can spend your time on what's going to be the final path that you go down. And the last thing that I want to share is just some useful resources. These 3 resources are really tremendous, and they're ever expanding. I feel like every time I go to them, they have more information in them, and they provide a really easy way to understand additive manufacturing and the key technologies and the key cost drivers in those technologies. And now I'm going to open it up for questions. First question that we have says, I saw that you guys can nest dynamically. Does that include 3D nested parts within selective laser sintering?
Yes, it does. We 3D nest by doing dynamic nesting in a single layer and stacking those layers as many times as possible within the build volume. So most 3D nests will dynamically nest each part in 3D space. And in order to account for the discrepancies between the full 3D nesting and our, in brackets, pseudo 3D nesting, we've allowed an override on the number of parts. So with SLS, we've set a high limit just based on the volume of powder, and because it can be 3D nest, and then in other parts the limit is actually restricted by the projected area onto the base plate.
Okay, awesome. Thanks, David. The next question that we have is, can we add other heat treatments to the costing in addition to the stress relief that you showed for DMLS?
Yeah, we can. There's our heat treatment cost model has a range of different processes in there. Off the top of my head, I can't remember them all, but there are at least, I think, maybe 7 or 8, and others can be configured if required.
Great, thanks. And yeah, all of you that are familiar with our existing heat treatment process group, all of those heat treatments are available within additive manufacturing, granted you're licensed to heat treatment. The next question is, do I need machining license to use additive manufacturing? The answer to that is generally no, but if you intend to use direct metal laser sintering, you do effectively need a machining license. And that's because all DMLS parts require at least some machining to clean up the base plate, as David talked about, and many of them, because they are high performance components, are going to require secondary machining to achieve the tolerances that you guys are looking for. So if you expect to be costing direct metal laser sintering parts, then yes, I would expect to use a machining license. David, this one is for you, and that is, can I cost parts with their support structures modeled in the CAD file?
The short answer is no. You could bring in support structures, but it wouldn't accurately model the cost of them, because we do apply certain properties to support structures, like the lattice factor, and our model wouldn't actually pick that up if it was already been brought in as a support structure. So what you really should do in that instance is model in your CAD system to shrink wrap the part, remove the support structures and shrink wrap the part, and then bring them in, and our cost engine will extract the support structures in.
Perfect. Thanks, David. I see a couple of questions up here about our future plans in terms of adding capabilities for the carbon machines that are used for those Additive shoes, and also a question about e-beam manufacturing. And right now, we don't have a definitive timeline that we can communicate to you, but if you're using those technologies or expecting to use them in the near future, definitely let myself or the aPriori support team know. Our roadmap is really driven by where you expect your businesses to go and what you expect to have a need to cost in the future. So if you're expecting to have that need in the future, just let us know. But right now, we don't have a timeline for those two things. David, this is a question for you, and that is, can I manually assign machining to geometry cost drivers within additive manufacturing?
Yes, you can. So it works in the same way as our casting or sheet metal components, where machining is a secondary process. And as I actually demonstrated, by applying a tolerance, the machining processes are automatically included. Or if they're not, if you don't want to assign a tolerance and you just prefer to see a machining operation on a feature, you can manually assign that by editing the operation. So yes, the answer is yes.
Okay, awesome. Thanks, David. So we're getting to the top of the hour, and I just wanted to wrap things up. Thank you very much for joining our webinar today.